So today we're going to cover section 4. We are going to learn about inscribed angles and inscribed polygons. So our first slide is a definition of what an inscribed angle is. So we've already saw the central angles, and those were the angles that had their vertex at the center. Our inscribed angles are going to have their vertices sitting on the side of the circle, the edge of the circle. So here it's an angle whose vertex is on a circle and whose sides contain chords of the circle. So notice here, this is the vertex of the circle and it's on the edge. And over here, these are chords. Now, I know they go out of the circle, but as far as creating the intercepted arc, these are chords that create it. And this is where the vertex sits on the side or the edge of the circle. Next slide. Theorem 10.7. We're still talking about this inscribed angle, but now we're going to talk about the measure of it. So the measure of an inscribed angle is 1/2 the measure of its intercepted arc. So before, when we had the central angle measure and its arc were congruent. Here, we're going to divide it by 2 or times it by 2, depending on what we're looking for. So for example, if I gave you this arc measure of AC to be 80 degrees, then I knew that its inscribed angle, that would be 80 divided by 2, or 1/2 of 80, and that measure of this angle here, this inscribed angle, would be 40 degrees. Now, remember when you had the central angle, if I put a center here, and I made a central angle, we would remember from before what we took the quiz on, the central angle and its arc are congruent, or they're equal. But the inscribed angle is 1/2 of the arc measure. So let's say I draw another circle here, but this time instead of giving you the arc measure, I'm giving you the angle measure. What if I told you this inscribed angle measure was 60? How much would this arc measure be? 120. 120. You just times it by 2. Good. Theorem 10.8. We're still talking about inscribed angles. However, if 2 inscribed angles of a circle intercept the same arc, then the angles are congruent. So I'm going to trace over some of the lines to show you where angle 1 is and where angle 2 is. So angle 1 goes here from the A over here to the edge and down to the B. That's how we create angle 1. Notice its intercepted arc is AB. Then if I were to trace out and create angle 2, it goes from A over here to the edge and then to B. Notice it also has the same intercepted arc of AB. So because they have the same intercepted arc, I know that angle 1 and angle 2 are going to be the same measure. So for example, if I told you the arc measure here was 100 degrees, how much would angle 1 be? 50. It's 1/2 of the 100. How much would angle 2 be? 50, because they're both the same, because they both have the same arc measure. So again, the inscribed angle is going to be 1/2 of its intercepted arc. Now we're going to talk about inscribed polygons and circumscribed polygons. An inscribed polygon is a polygon with all of its vertices on a circle. So basically, think of the word inscribed like it's saying the word inside. So this first picture, the triangle is inside the circle, so it's inscribed. It's an inscribed triangle. When we talk about it reversed, and we're talking about in terms of the circle, we're saying a circumscribed circle is the circle that contains the vertices of the inscribed polygon. So So it's like the circle is outside of the polygon. But if we're talking about the triangle is inside, it's inscribed, the polygon. So basically, both pictures are saying the same thing, but if you're referencing the polygon or versus referencing the circle. Next, Theorem 10.9. This theorem states, if a right triangle is inscribed in a circle, so this triangle is inside the circle, then the hypotenuse is a diameter of the circle. So if you have a right triangle and it's inscribed, meaning that right angle is on the side of the circle, then its hypotenuse will be the diameter. The converse of that is if one side of an inscribed triangle is a diameter, then the triangle is a right triangle. And the opposite the diameter is the right angle. We're going to use this in our proof today. So here it's saying that the measure of ABC equals 90 if and only if AC is the diameter of the circle. All right. Anybody know how I could figure out the arc measure of AC? It's 180, right? Because the endpoints here, it's a semicircle. Okay. I also just saw from the theorem that angle B here, because the hypotenuse is the diameter, this is a 90-degree angle. And remember, we just saw the theorem that stated the inscribed angle is half the measure of the arc. So if I knew that this was 90, I could have also found the arc measure by timesing it by 2. So there's going to be multiple ways to find out these different measures. Theorem 10.10. Here it's stating a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So if we have angle 1 supplement to 3, or angle 2 and angle 2 supplement to 4, then we know this quadrilateral could be inscribed in the circle. Okay, so if the opposite angles are not supplements, then it cannot be inscribed. Next slide. Useful fact number 1. An angle inscribed in a semicircle is a right angle. And we saw this theorem. So we could see here that if it's inscribed in the semicircle, notice our hypotenuse is the diameter, then angle 1 is a right angle. So if it's inscribed in the semicircle. Useful fact number 2. The measure of an angle formed by a chord and a tangent is equal to half the measure of the intercepted arc. So sort of like the inscribed angle, but remember the inscribed angle was created by 2 chords. This one's going to be created by the chord and a tangent, and it's still half of the measure of the arc. So for example, if I told you that this arc measure of A to B was 130, how much would angle 1 down here be if it's half the measure of the arc? Angle 1 would be 130 divided by 2, 65. All right, what if I add an angle 2 here? How could I find the measure of angle 2? What could I do? Okay, I could do 180 minus 65. That's going to give me the measure of angle 2. So subtract here, and I get 115. Good. That's going to give, because it's sitting on a straight line. Did everybody see that? 1 and 2 together. How much would its arc measure be? Good. Double it or times it by 2, and it would be 230 degrees. Now, another way we could have gone about this is we could have also taken the 130 arc, subtracted it from 360, found the arc measure and then divided it by 2 to get the angle. So there's more than one way to solve these. Again, think of them like puzzles, fill in the missing pieces. The intercepted, example 1. So let's look at part A first. We need to find the values of x and y in this circle 0 or circle O. Okay, so let me outline these angles that I see here. So I've got an angle here for y, and y is referring to this. So here is y. I also have an angle here. I've got an arc length here for x. That's what x is going to be. So let's see. Let me highlight the letters after I've... And then this will be blue. And then I also have this inscribed angle here. That's 20 degrees. So right here is 20 degrees. So what can I figure out? How much will x be? How can I find out the measure of x?
20 times 2.
Good. 20 times 2, because we know that the intercepted arc is twice the value of the inscribed angle, so that would be 40. All right. How can I find the measure of angle y?
110 divided by 2.
Okay. Now, notice the...
150 divided by 2.
Beautiful. Okay. He had to add the 110 and the 40 because that's where angle y, that's where the intercepted arc is. So 110 plus 40, and then divide that by 2. And we would get the angle measure to be 75 degrees. So y equals 75. Good. So these pictures are going to get a little bit more complicated. And, it's going to be helpful if you, overwrite or shade in what you're looking for. Let's look at the picture in B.
Wait, how'd you get 75?
So we knew that this was the angle that we were looking for, y, right here in blue. So we knew its intercepted arc was right here, and it was the 110 plus the 40. And then I got 150, and then I divided it by 2. Because I know that the inscribed angle is half of its intercepted arc measure. Okay, let's go over to figure B. Again, we're looking for the values of x and y. So I'm going to go ahead and outline each one again. So I have angle x right here. And then I have angle y, which is going to be here and to here. So, any suggestions or anybody know how we can find either x or y? All right, so we can start filling in our circle. We've got 40 here because that's going to be the corresponding. Wait a minute, what am I doing here? Okay, so we have the intercepted arc here for the 20-degree angle, and that's going to be 40. Okay, that's a start. All right, what else could we do? Anybody see what we can do with the diameter? Anybody see the semicircle arc there?
The two vertical angles, those are 90. The vertical angles.
Where are the vertical angles?
Under y. Because you said that if it's in a semicircle, then it's a right triangle.
Okay, good. But angle y is going to be the 90-degree angle. Okay, so when it's in a semicircle, when you have a right triangle or a triangle inscribed in a semicircle, then we know it's a right triangle, and angle y is our right angle because the hypotenuse is our diameter. So angle y is 90 degrees. Also notice we have the diameter that's going across here. So this is a semicircle. So we've got 180 degrees here. And notice the intercepted arc of this angle here is at the ends of the diameter, so it's 180 degrees. If I divide that by 2, it gives me the 90. Okay, then for the x, since we found the intercepted arc of this 20-degree angle, this green one, notice the intercepted arc is the same for angle x. It's still this 40 degrees. So angle x is going to be half of 40, and it's going to be 20. Okay, so that very first theorem we saw that the two angles are going to be congruent when their intercepted arc is the same. So the 20-degree angle here and this x, they both are 20 degrees because they both have this intercepted arc. It's the same for both. So y equals 90 and x equals 20 in this figure. Everybody good on picture B? Okay, next slide continues example 1. All right, let me fix this back. Okay, so we have the 70-degree angle because it's the 140 divided by 2. Then we also found this intercepted arc, which is 120. And then we're going to find the other missing piece, and we'll do 140 plus 120, get 260, subtract that from 360. And I know the other piece of the arc to complete the circle will be 100. Okay, so now, Kimberly, you had a question?
Yeah. Could you have just found the triangle example? You have 70 and 60, and then that would be 130, and then you have 50, and the same thing, multiply 50 by 2.
Exactly. So another way you could have found this 100-degree arc measure is add the two angles in the triangle, subtract them from 180, find out it's 50 degrees, and then times that by 2 to get the 100. So yes, there's more than one way to fill this in. All right, so now that we have a lot of information, now maybe we can go back and find the values of x and y. So the value of x and y can be found using that same theorem, that when you have the tangent and the chord, we know that its angle measure is going to be half of its intercepted arc. So the value of x will be, anybody? 60. And the value of y will be 50. All right. Another way you could have done this is once you found x or y, maybe you didn't have an arc measure. Notice that these three angles are sitting on a straight line. You could have added them and subtracted from 180. Again, multiple ways to fill in this circle. Yes?
Wait, how did you get the 120 and the 100?
Okay, so for the 120, I saw that this angle here, the 60 degrees that was originally given to me, that's going to be this arc measure, and or this angle measure. So the inscribed angle was 60. So I knew its intercepted arc measure is going to be twice the 60, which is 120. Then to find the 100, I went ahead and added the two arc measures I had, the 140 and the 120, and got 260, and then subtracted from 360 to get the 100. Okay, figure D. What are we going to do here? Any suggestions, Kimberly?
Divide 80 by half.
Okay, so we're going to either multiply 80 by half or divide it by 2 to find x. So 80 divided by 2 gives me 40 degrees for x. All right, now what can I do? David?
Well, you start with 1/2 of the circle, which is a semicircle. Then you just subtract 80 from 180.
Beautiful.
100, and then divide it by 2.
Good. All right, he realized that this was a semicircle arc, because here's our diameter at the endpoints. So 180 minus 80, and that's going to give me this arc measure right here. From here to here is 100. All right, so then now, what else can I do? Yes?
Couldn't you just, since it's diameter, it's cutting in half their corresponding angles?
Okay, what we can say here is, well, this other side is going to be 180 also, but we need to know a smaller piece. We need to know why. But notice there was a theorem that we learned that when you have two congruent chords, their corresponding arc measures are congruent also. So if this arc over here is 100, which is the intercepted arc for this chord, then this one here is also 100. So then once I find the intercepted arc for angle Y, which is 100, I can divide it by 2, and I know Y is 50. Okay, so the last slide is a proof. Here are, let me make it smaller so I can get everything in here. So over here we have statements. All right, statements, reasons. All right, so the first statement is going to be our given information. So we have circle O congruent to circle P. We also have arc AC congruent to arc AB, and that's given. Statement 2, I'm going to first start out by showing that the radiuses are all congruent. So I'm going to start by saying that DO is congruent to OA, which is congruent to AP, which is congruent to PE, because I can do that by definition of congruent circles, that all radiuses are congruent. So here I'm going to state that DO is equal to OA, which is equal to AP, which is equal to PE. And this is definition of congruent circles. Next, notice I had congruent arcs here. So I could also state that AB is congruent to AC because congruent chords have congruent corresponding arcs. So here I could say AB is congruent to AC, and I could say congruent chords have congruent arcs. See that we have angle B and angle C are going to be right angles because those are triangles that are inscribed in the semicircle. So I'm going to state that angle B is equal to angle C, which is equal to 90. And what this reason is, if an inscribed triangle intersects a diameter, or is inscribed then a diameter, then it's 90 degrees. Now have a right angle here and a right angle here. Now, can I prove triangles with angle side side? Is that a valid postulate? Angle side side. Is ASS a valid postulate? No, it's not. So I need to find some more stuff in here to prove these triangles congruent. So notice, because I have those congruent arc measures, I know that I can say that angle BDA and CEA are going to be congruent because they have the same arc measure. But it's going to take several steps. So for this one, now I'm going to say, for step 5, I'm going to say that angle CEA is equal to half of the measure, or half of the arc measure of AC. I'm also going to say that angle BDA is equal to half the measure of arc AB. So this is going to be the inscribed angles is equal to half the arc measure. Okay, now I could say that angle CEA is congruent to BDA by substitution. Now I actually have another angle here. So this angle is congruent to this one, and this one to this one. Now I actually have a shortcut, and I can use angle, angle, side to show that these two triangles are congruent. So I would have to state now the proof ABD is equal to or congruent to triangle ACE, and I'm going to use angle, angle, side. Now, we could have gone in there and found the diameter, and we could have used side, angle, side. So there's more than one way to prove that these triangles are congruent. But when you make your steps, it needs to be justified with a theorem or a definition or something.